Session 1, Introduction to Soil Characteristics. Today we'll explore the fundamental characteristics of soils in geotechnical engineering, focusing on how we classify, describe, and analyze soil properties. Understanding soil characteristics is essential for civil engineers because soil serves as the foundation for nearly all structures. Whether designing buildings, roads, bridges, or dams, engineers must understand how soils behave under various conditions to ensure structure stability and safety. Poor soil characterization can lead to numerous engineering failures, as demonstrated throughout the world in some of the pictures that we'll be encountering during this course. From catastrophic settlement failure, slope failure, and landslides. The learning outcomes in this session will include a definition of soil from a civil engineering perspective to distinguish between different soil formation processes, analyzing and interpreting particle size distributions, and understanding the concept of plasticity in fine soils. Finally, we will introduce the Australian Soil Description Standard and Classification System. Let us begin by examining what constitutes soil in engineering terms, then explore how we analyze particle size distribution, and then we can discuss plasticity of fine soils and conclude with soil description and classification systems used in the AS 1726 guidelines. In civil engineering, soil is defined as any uncemented or weakly cemented accumulation of mineral particles formed by the weathering of rocks, with void space between particles containing water and/or air. The weak cementation may come from carbonates, oxides, or organic matter. Soils can be characterized by their formation processes. 1. Residual soils, which are weathered products that remain in their original location. 2. Depositional soils, or transported soils, weathered products moved and deposited elsewhere by gravity, wind, water, or glaciers. The weathering process that creates soil from parent rock can be either physical or chemical. Physical weathering produces particles that retain the same composition as the parent rock. These bulky particles can be angular, rounded, flat, or elongated, and range in size from boulders to fine rock flour. They typically form a single grain structure where particles contact each other directly without bonding. Their packed state can be described as dense, medium dense, or loose. Chemical weathering changes the mineral formation of the parent rock through interaction with water, especially if that water contains an acid or a base. Further chemical interaction can include interaction with oxygen and carbon dioxide. This process will create a crystalline particle structure of colloidal size, typically known as clay minerals. These minerals are less than 0.002 millimeters in diameter. Soil particles vary tremendously, from over 100 millimeters to less than 0.001 millimeters, and are classified into specific ranges, the smallest being clay, then, in ascending order, silt, sand, gravel, cobbles, and boulders. While these terms define size ranges, they also describe soil types. Most soils consist of graded mixtures from multiple size ranges. It is important to note that clay mineral particles, even in small proportions, can significantly influence soil properties. Soils are broadly categorized as cohesionless and cohesive. You will also hear cohesionless soils referred to as coarse soils. Cohesive soils are often referred to as fine-grained soils. Fine-grained soils have properties that are influenced mainly by the interactions of the clay and silt-sized particles. Coarse soils have properties influenced mainly by the large sand and gravel-sized particles. Particle size analysis can determine the percentage by mass of particles within different size ranges. This distribution is crucial for predicting soil behavior. For coarse soils, sieving is the primary method. It is undertaken by passing the soil through a standard test sieve with progressively smaller and smaller mesh sizes. This will determine the mass retained in each sieve, from which we can then calculate the accumulative percentage passing through each sieve as a fraction of the soil that we begun with. For soils containing fine soil particles, which are clays and silts, we treat them with a chemical agent referred to as a deflocculating agent and wash through the sieve. For fine soils and the fine soil fraction of a coarse soil, sedimentation is used. It is a process based on Stokes' law. You'll be familiar with this if you have a snow globe, where if the snow globe has large particles and fine particles, when you agitate your snow globe by shaking it up, it will take longer for the fine particles to settle out of the snow globe. To do so in a lab, we pre-treat the soil with hydrogen peroxide to remove organic material. We create a suspension in distilled water with a deflocculating agent. Then we place the suspension in a sedimentation tube, and we calculate sediment times for particle sizes. We take samples at specified depths and times to determine the particle size distribution. The particle size distribution is typically presented as a curve on a semi-logarithmic plot, with the y-axis showing the percentages of particles smaller than the size shown on the x-axis. The shape of this curve reveals important soil characteristics. Well-graded soils are smooth, concave distribution curves with no excess of any size range and no missing intermediate sizes. Poorly graded soils are either uniform, constituted by only a single particle size, or gap-graded, which means particles of small or large size with no intermediate sizes. Key parameters derived from the distribution curve include D10, which is the effective size, and refers to particle sizes that are 10% of particles, being smaller than that nominated size. The coefficient of uniformity, Cu, which is the ratio of D60 to D10, indicating the spread of particle sizes, and the coefficient of curvature, Cz, which describes the shape of the distribution curve. You find it very hard to follow this verbally, but when you have a look at the graph, you'll see that these D10, Cu, Cz, and D60 points are just areas of the curve, or points on the line. Plasticity of fine soils is a critical characteristic. It describes their ability to undergo unrecoverable deformation without cracking or crumbling. Depending on water content, a soil may exist in one of four states: liquid, plastic, semi-solid, or solid. As water content decreases, soils transition from liquid through plastic and semi-solid states to a solid state. The water content at which these transitions occur varies between soils. In the ground, most fine soils exist in the plastic state. Plasticity results from clay mineral particles, or organic matter, that create very small void spaces, allowing water to be held at negative pressure by capillary tension. This produces cohesion between particles, enabling the soil to be deformed or molded. Absorption of water due to surface forces on clay minerals may contribute to plasticity. Important plasticity parameters include 1. Liquid limit, 2. Plastic limit, 3. Plasticity index, 4. Liquidity index, 5. Activity. The liquid limit is the upper water content boundary of plastic behavior. The plastic limit is the lower water content boundary of plastic behavior. Meaning that if we add more water past the liquid limit, our soil will behave as a liquid. The plastic limit describes the point where if we were to subtract any more water, it would cease to behave as a plastic and would behave as a semi-solid. The plasticity index, IP, is the range of water content where soil exhibits a plastic behavior. For clay, we can think of this as the water content range where the soil is able to behave like Play-Doh. The liquidity index, liquid index, represents the natural water content relative to the liquid and plastic limits. The activity ratio is the ratio of plasticity index to the percentage of soil clay-sized particles, expressing the degree of plasticity of the clay fraction. Soil description and classification. A standardized language for soil description is essential for effective communication in geotechnical engineering. This is provided in Australia by the AS 1726 guidelines, which also make use of the Unified Soil Classification System, the USCS, which is used globally. A comprehensive description includes both material descriptions and in-situ mass characteristics. Material characteristics can be determined from disturbed samples, preserving particle size distribution, but not structure. They will be presented in two forms. The first is the primary soil, which is the particle size dominant within the soil sample. This will be highlighted in all capitals. The secondary soil component will describe the color, particle size, texture, or alternatively, a second major composition of the soil. For example, a sandy clay would be referred to as sandy, lowercase, clay, all caps, where clay is the predominant soil component. Mass characteristics are ideally determined in the field or from undisturbed samples, in situ compactive states for coarse soils, or stiffness for fine soils. We'll find out more about how we recover in situ samples so that we can examine them in the lab. But for now, we can just think of coarse soil samples as being removed without being disturbed, either through a test that is conducted in the field, on the soil, in the ground, or by means of soil recovery. This is frequently undertaken for fine-grained soils by pushing a tube down into the soil so that we can then push out the same soil in the lab. Other mass characteristics include bedding or discontinuities or weathering of the soil profile. They include soil macrofabric features, such as thin layers, fissures, and inclusions. It's important to distinguish between soil description and classification. Soil description includes both material and mass characteristics, making each soil description relatively unique. Soil classification allocates soil to one of a limited number of groups based on only material characteristics. Hence, our soil description may include regionally significant descriptions in our AS 1726 guidelines. The soil classification will allocate our soil to a limited number of groups, provided and identified for us by the Unified Soil Classification System. It is these soil classifications that will be used by an engineer when they use a finite element analysis program. Or, in your workplace, you may have some of these composed for you in an Excel spreadsheet. This is why soil classification is particularly useful when soil will be used as a construction material. It allows engineers to draw on past experience with similar soils and to apply them to the soils that are presented to them on site. Rapid assessment procedures. While laboratory tests provide precise measurements, field situations often require rapid assessment of soil properties. Particle sizes of 0.06 mm particles are just barely visible to the eye and feel harsh but not gritty. 2 mm is the boundary between sand and gravel. When we undertake soil descriptions in the field, we use a method known as a visual tactile method, and it's limited to the sense perceptions of the person who is undertaking the soil description, as well as their prior experience in distinguishing between two similar soils. Our plasticity assessment that we undertake in the field includes 3 tests: toughness tests, which include rolling soil into threads to assess stiffness and brittleness; a dilatancy test, which observes how water appears when we pat the soil or shake it; and a dry strength test. A toughness test, by rolling soil into a thread, can be conducted by placing our clay onto the carbonate and rolling it into a thread and seeing how long it will take before it breaks. A dilatancy test we can think of visually when we go to the beach, and as we walk along the sand near the waves, the water underfoot will dissipate due to the pressure of our foot. It is a different mechanism that applies at the beach because sand is a coarse-grained soil and clay is a fine-grained soil. But in principle, visually, we can see the connection. For the dry strength test, we assess the strength of a completely dry soil sample. This is often colloquially referred to as the biscuit test, which is where we form a biscuit of our soil and we see how strong it is to break. Soil classification systems. Classification systems group soils based on grading and plasticity. In Australia, soils are divided into groups with letter symbols representing main and qualifying terms. The boundary between coarse and fine-grained soils is taken as 35% fines content. That means that if we believe that there is more than 1/3 clay or silt in our soil sample, it is classified primarily as a cohesive or fine-grained soil. Fine soils are classified using the plasticity chart, as mentioned previously, which plots plasticity index against liquid limit. The chart defines soils into zones designated by letters, with a diagonal A line that separates clays above from silts below. You can see this chart in our course notes. The letter denoting the dominant soil fraction appears first in the group symbol, followed by qualifying terms. Organic content is indicated by a suffix O. For example, a well-graded sand is referred to as a SW. A sandy clay would be referred to as a CI, because it has an intermediate plasticity. In this session, we've explored the fundamental characteristics of soils from an engineering perspective. We've learnt how soils form through weathering processes, how to analyze particle size distributions, the concept of plasticity in fine soils, and the standardized system for soil description and classification. These concepts form the foundation for understanding soil behavior in engineering applications. In our next session, we'll build on these fundamentals by exploring phase relationships in soils and the principles of soil compaction. Understanding these concepts will allow us to analyze soil behavior under loading and predict how soils will perform in various engineering situations. As a takeaway, consider a soil sample you might encounter in the field. How would you approach describing and classifying it? And what specific characteristics would you look for to determine if it would be suitable as a foundation material for a small building? Think about how the rapid assessment techniques we discussed and what laboratory tests may be most informative. Not all of this information has been presented to you within this audio file. You will need to read your course notes, in addition to attending sessions in class, to have a full and thorough understanding of this subject.